Hello everyone and welcome to another video on our own devices. I'm Mk.II and today we are looking at a type of device that shows up quite often in popular media. These are three types of blasting machines which you may have seen in various films or cartoons being used to set off explosives. Despite the popular association of these machines with the likes of the Looney Tunes, these are practical real-world tools that have been in use for over a century and a half. So, without further ado, let's have a closer look at these and let me show you exactly how they work. Now, the development of the blasting machine is inextricably tied with the development of practical high explosives. Now, for centuries, the only explosive of any kind in use was black powder, likely developed around the 9th century CE in China and composed of charcoal, sulfur, and potassium nitrate, aka saltpeter. Now, for over a millennium, black powder was used as a propellant for firearms, as an explosive filling for artillery shells and other weapons, and as a blasting agent in the construction and mining industries. However, it did have a number of drawbacks. For one thing, it was extremely hygroscopic, that is, it readily absorbed moisture from the atmosphere, but also black powder is classified as a low explosive, meaning that rather than detonating, it simply deflagrates or burns rapidly, producing a large volume of hot, high-pressure gas. As such, it needs to be tightly contained in order to have any explosive force at all, and the amount of pressure it can produce is highly limited, making it only marginally useful as a blasting agent, especially for hard rock. Now, while the first high explosive was technically fulminating gold, which was known to alchemists as early as the 15th century, the first practical, mass-produced, and mass-used high explosive was nitroglycerin, discovered by Italian chemist Ascanio Sobrero in 1846. Composed of nitric acid, sulfuric acid, and glycerin, unlike gunpowder, nitroglycerin actually detonates, producing a much more powerful supersonic blast wave. But as most of you are probably aware, this power came at a high cost, as nitroglycerin is infamously sensitive to shock and heat, and very easy to accidentally set off. And indeed, Sobrero soon came to regret his discovery and actively warned against its use in industry. But his warnings fell on deaf ears, and the substance was quickly adopted in the mining and construction industries. Now, one of the first firms to mass-produce nitroglycerin commercially was Alfred Nobel & Company, founded in 1865 by Swedish industrialist Alfred Nobel. However, the extreme danger of this product was quickly exposed by a series of deadly accidental explosions, including one at the Nobel factory in Heleneborg, Sweden in 1864 that killed Alfred's younger brother Emil. This tragedy, along with new laws banning the transport of nitroglycerin in several countries, spurred Nobel to try and tame this volatile substance. After much experimentation, in 1867, he finally hit upon the method of mixing nitroglycerin with kieselguhr, a type of absorbent diatomaceous earth found in the Kummel Hills around Nobel's factory in Gstaad, Germany. This phlegmatized the explosive, making it much more shock-sensitive and safer to handle and transport than raw nitroglycerin. Nobel dubbed it Dynamite, and this invention made him a millionaire and revolutionized the mining and construction industries. However, it still wasn't a perfect solution, as improperly stored dynamite tended to sweat nitroglycerin, making it extremely hazardous to handle. As a result, in 1875, Nobel developed an even more stable explosive called blasting gelatin, composed of a mixture of nitroglycerin, nitrocellulose or gun cotton, potassium nitrate, and wood pulp. Now, the history and chemistry of nitroglycerin, blasting gelatin, and other early explosives is a fascinating topic in its own right, but a bit outside the scope of this video. However, if you want to learn a bit more about them, please check out these videos I wrote over on Today I Found Out, links in the description. Also, if you're looking for some good movies to watch, you should check out Henri-Georges Clouzot's 1953 thriller The Wages of Fear, and William Friedkin's excellent 1977 remake Sorcerer, both of which center around the transport of nitroglycerin or dynamite over a dangerous mountain road. Anyway, getting back to our story, while dynamite and blasting gelatin were a lot safer to transport and handle than raw nitroglycerin, they were also much harder to set off intentionally. Thankfully, Alfred Nobel had already developed the blasting cap for setting off nitroglycerin charges. This comprised a metal tube containing a small black powder charge connected to a lengthened safety fuse. In 1867, Nobel replaced the black powder with the more powerful primary explosive mercury fulminate, which generated just enough of a shock to set off dynamite and blasting gelatin. Just 1 year later, in 1868, American inventors Henry Smith and Perry Gardner improved upon Nobel's design by creating a fulminate blasting cap that could be set off remotely by an electric current rather than a length of burning fuse. Henry Smith also patented a manually operated blasting machine for setting off said caps. That basic design remained relatively unchanged for over a century and forms the basis of two of the units that we have here. So let's actually have a closer look at these and let me show you how they work. Right, so the first blasting machine we have here is a civilian example manufactured by the Dominion Electrical Works of Halifax, Nova Scotia. And that's about all I know about it. I unfortunately wasn't able to find any commercial information about this particular unit or the company that made it, though if I had to guess when this was manufactured, based on the general style and construction methods, I'd say no later than the 1930s. Though, as always, if any of you watching know any more about it, please let me know and I'll add the additional information to the description of this video. Anyway, this is a very simple unit to use. You simply attach your lead wires that lead to your blasting caps and explosives to these terminals on the top. You then raise up the plunger and then push it down firmly, like that. Now, if we undo these screws on the side and remove the end panels, we can see what's going on inside. As you can see, on the side of the plunger is a rack gear, which engages with this pinion gear to translate the vertical motion of the plunger into rotational motion that drives this generator. Now, this particular generator is a dynamo, which uses a commutator with two copper brushes to reverse the polarity of one side of the AC sine wave, converting it into DC. So you'll notice that there's no ratchet or other mechanism to disengage the rack and pinion gear when the plunger is being withdrawn, meaning that the plunger will drive the generator in both directions. So what prevents you from accidentally setting off your charges prematurely when withdrawing the plunger? Well, that is taken care of by this switch, which is closed by the plunger as it reaches the bottom of its stroke. This prevents any current from flowing through the fire circuit unless A, the plunger is being pushed in the correct direction, and B, the dynamo is fully spun up, preventing misfires. And for this reason, a lot of instruction manuals told you to try pushing the plunger all the way through the bottom of the machine to ensure a successful blast. And by the way, while most plunger-type blasting machines are operated by pushing the plunger down, pull-up versions also exist, as do smaller handheld units operated by twisting the handle. Blasting machines like these typically came in a variety of sizes differing in maximum voltage output and were rated and advertised based on how many series-connected blasting caps they could set off simultaneously. For example, a small handheld twist machine could set off maybe 4 or 5 caps, while some of the larger machines could set off up to 150. Though, unfortunately, because I don't have any catalog information on this particular unit, I don't know exactly what this one is capable of. Now, before we move on, there is one feature of this machine that had me stumped for quite some time, and that is the fact that it has 3 rather than 2 electrical terminals. And no matter where I looked, I found that this was a very rare configuration, that pretty much every blasting machine that has ever been made has only 2 terminals, and I couldn't find any reference explaining why this one should have 3. Now, looking at the circuitry, I saw that one of the terminals is attached to one side of the switch at the bottom, meaning it's probably the ground or return, while the 2 others are connected to the dynamo output. And I theorized that maybe this allowed you to connect only one terminal in order to test the fire circuit, but you had to connect both in order to actually fire your explosives. However, I finally came across a 1911 copy of Dupont's Farmer's Handbook, which covers the use of explosives for stump removal, ditching, and other tasks around the farm, and this finally gave me my answer. Apparently, 3-terminal blasting machines had to be special ordered, and what these allowed you to do was connect your 2 output terminals to the ends of your blasting cap string and the ground or return terminal to the middle. This halved the electrical resistance of each side of the circuit, allowing more blasting caps to be set off than with a 2-terminal machine of the same size. Now, I suppose you could accomplish the same thing by simply adding another connecting wire to one of your lead wires, but I guess this makes things a little neater and tidier. And of course, you can use this as a regular 2-terminal machine by simply attaching one lead wire to your ground or return terminal and then attaching the other to one of the other powered terminals. Anyway, moving on, this is another plunger-type blasting machine, albeit a much more compact model designed for military use. This is an Exploder's Dynamo Mk.VII, and this was the standard blasting machine for British Commonwealth forces during the Second World War and for at least a decade afterward. Unfortunately, I haven't been able to determine when this particular example was manufactured, though the oldest dated unit I found was made in 1939, so it's likely that these were adopted just prior to the outbreak of the Second World War, maybe in 1937, along with a lot of World War II British equipment. Now, the Mk.VII was manufactured by a wide variety of companies, including G.D. Peters and Company Limited of London, England, Electricity Meter Manufacturing Company Proprietary Limited of Sydney, Australia, and Foreign and Deed Proprietary Limited of Melbourne, Australia. The example I have here is only marked GK, but I haven't been able to find any companies of that name anywhere in the Commonwealth likely to have manufactured a device like this. However, since I found this one here in Canada, it was likely manufactured in Canada or at the very least used by the Canadian military. Though, as you can see, the original military serial number on the data plate has been struck out and replaced, suggesting it may have passed into civilian hands after the war. But again, if any of you know more about this than I do, please let me know. Anyway, like the Dominion machine, this is actually quite simple mechanically, but far more robust and with a number of neat design features. The body is made of cast aluminum and features heavy-duty rubber seals on all joints to prevent water ingress. Most units, though not this one, were fitted with a brass plate on the bottom bearing the inscription, "To ensure water tightness, screw fixing screws fully home and fill cavities with compound," the compound in question likely being some sort of putty or mastic. Right, so on the top we have our two electrical terminals and a folded carrying handle, which also doubles as our firing plunger handle. To use this, we simply push down and twist the handle counterclockwise to disengage the bayonet connector, and it just pops off like that. We then unscrew this brass cap to reveal the head of the plunger, then insert and twist the handle clockwise to lock it in place. Then, just like with the Dominion Electrical Works unit we just looked at, we withdraw the plunger and push it down firmly to generate and transmit our firing signal through the lead wires connected to the terminals. And by the way, if the plunger cover is stuck, then the carry or plunger handle includes a convenient wrench end to help you out. Right, to disassemble the Mk.VII, we first undo these screws at the bottom. Originally this would have had 6, but 4 have gone missing. We then unthread this brass collar around the plunger, and then the top cover comes off just like that. And originally there would have been a thick rubber gasket along this main seam, but that has since crumbled to dust. Also, on the inside of the top cover, you can see this pair of shiny contacts connected to the terminals, and these connect to the dynamo via these two spring-loaded contacts. Mounted to the base plate, we have our generator, which once again is a DC dynamo with a commutator, though instead of simple copper brushes, this one uses spring-loaded carbon brushes. As in the Dominion Electrical Works blasting machine, the dynamo is driven by a rack and pinion gear, only the Mk.VII includes a ratchet and pull mechanism that prevents the dynamo from spinning backwards when the plunger is raised. And we can see how that works by disassembling this housing here. However, the Mk.VII also uses a plunger-activated switch to close the circuit at the bottom of the plunger stroke and send the firing pulse through the terminals. Now, the regular Mk.VII was capable of setting off 12 number 33 standard detonators connected in series at the end of 365 meters of wire, while the upgraded Mk.VII Star upped the number of detonators to 42. Now, the third and final blasting machine we're looking at today is a bit of a different one. This is an Exploder Dynamo-Condenser Mk.II, or maybe a Mk.III, but we'll get to that in a minute. Now, this style of blasting machine is popularly known as a Beethoven exploder, reportedly because when they were first tested in mines, the rhythm of the explosions reminded the operators of the opening bars of Beethoven's Fifth Symphony. Now, Beethoven exploders are a trademark of Arbor Instruments of Wrexham, England, though this particular unit was made by Berger Engineering, a subsidiary of Imperial Chemical Industries Limited, and its design appears to be based on a 1945 patent by one William Albion Mutter. Now, the carrying handle on this unit is stamped MEC 1951, but this refers to the Mills Equipment Company, a major manufacturer of webbing for the Commonwealth Armed Forces, and the handle may not have been manufactured at the same time as the exploder itself. So how this works is that you turn a crank handle on one end to turn a generator which charges a large capacitor or condenser, which can then be discharged through your lead wires by pushing a button. So to set this up, we flip open the spring-loaded cover on the end and insert and thread in our crank handle. And when we remove the handle, this cover not only prevents dirt and dust from entering the unit, but also activates a switch that A, opens up the firing circuit, preventing accidental discharges, and B, bleeds off any charge remaining in the capacitor through a set of resistors. So in this sense, the crank handle also doubles as a safety key. Anyway, once our crank is attached, we turn it clockwise until the neon lamp behind this window on top glows red, indicating that the capacitor is fully charged. We then push this rubber button to discharge the capacitor through the firing circuit and set off our explosives. At the other end of the unit are our electrical terminals for connecting our lead wires, which are of the spring-loaded push-button type. As issued, these units were supplied with a fusion box tester device that fit over these terminals and used either a fuse wire or a light bulb to test the function of the capacitor. We can also see below the terminals the molded-in words Exploder Dynamo-Condenser Mk.II WA10761. But if we look at the metal data plate on the side of the unit, it identifies this as a Mk.III. So which is it? Well, if we open this up by removing all these screws on one end and sliding out the chassis, we can see that the internal data plate reads Mk.III and that the circuitry itself is different from the Mk.II. In the Mk.II, the crank turns a Type 26A 75-volt magneto generator, the output of which passes through an autotransformer and what is known as a Gyneka voltage doubler circuit. This comprises a pair of capacitors and diodes or rectifiers arranged so that it outputs direct current at twice the voltage of the input alternating current. The autotransformer and voltage doubler circuit together generate 1800 volts DC, which is stored in a 6 microfarad capacitor. This circuit, on the other hand, is considerably simpler. There is no voltage doubler circuit, just a generator C Mk.II, autotransformer, and a half-wave rectifier that outputs 1500 volts DC, which is also stored in a 6 microfarad capacitor. Add to this the fact that the terminals on the Mk.II are of the screw rather than the push-button variety, and this leads me to conclude that this is actually a Mk.III that has had a Mk.II shell grafted onto it, likely because a proper Mk.III shell wasn't available. Weirder things have happened in repair depots. Now, some other details to point out in here are the neon lamp to indicate the charge of the capacitor, and the mechanism attached to the swinging crank handle port cover, which, as you can see from the schematic, opens switches K3 and K4 that connect the main capacitor to a bleed resistor. K5 is also closed by turning the crank handle, allowing current from the generator to flow into the capacitor charging circuit. Finally, pushing the fire button closes switches K1 and K2, discharging the main capacitors through the lead wires to set off the explosives. Now, hand-cranked Beethoven units are still made by Abra Instruments today, though most of their and other firms' blasting machines now tend to be battery-operated. Also, in a lot of demolition work, nodal or shock tube detonators composed of flexible plastic tubing with a thin explosive lining are used to transmit firing impulses to the explosive charges. However, all these are subjects for future videos. Now, long-term viewers of the channel will recognize that this is a remake of an older video that I put out around 2 years ago. Now, in that video, I think I tried to cover way too much ground and ended up making a lot of technical errors as a result. So this time around, I decided to focus more closely on the machines themselves rather than covering the entire history and technology of blasting equipment. However, in the future, if I do come across other pieces of blasting equipment like different types of blasting caps or other styles of blasting machines, I will, of course, cover them in more details. But for now, this is all I have for you today. Thank you so much for watching, and I'll see you next time in another video where we'll look at yet more explosives technology and other fascinating devices just like these. Until then, I'm Mk.VII from Our Own Devices. Have a great day.